To welcome you to the joint seminar of two online seminar groups, the optimization seminar and the seminar on methods, what is the official name? Analytical methods for arbitrary data sources. So it is our pleasure to have today Francis Bach talking in our joint seminar. I think Francis is a well-known researcher, is a very prominent mathematician working in optimization, but also in data science, machine learning, and very new hot areas. Gianbattista Ruti posted some interesting information in the chat. And so Francis Bach is the first winner of the so-called of the Moreau Prize. It is a prestigious prize in France. Awarded by SMI and the National Academy of Sciences. And Francis was, this I want to say, this I find very interesting. He was supposed to give the end of April a prestigious talk in Paris 6 in the Academy of Sciences. This was canceled, I guess. And yeah, Jean-Baptiste thinks that our joint seminar is a good substitute for this. So welcome, Francis. Thank you for accepting our invitation. So the rules are the same as in the last 2 weeks. So you can ask questions, just let us know in the chat or raise your hand, and we will interrupt the speaker. You can ask your questions. Though, of course, there will be questions at the end of the talk. So Francis, the stage is yours.
Okay, so can you see my screen?
Yes.
Okay, so first, I would like to thank the organizers for inviting me. It's a real pleasure to give a talk from my bedroom. So before I start, so I've given instructions not to be disturbed, but as all attendees with children will know, sometimes it does not work. But this being said, I hope to be left alone for 1 hour. And before I start, I would like to acknowledge the amazing work of my colleague, Lenaik Shiza, who's behind most of the ideas I'm going to present today. So today, I'm going to consider supervised learning, like a parametric framework, where I'm given some observations, xi, yi. Xi can be an image, yi can be a label on that image, and the goal is to predict y given x for a new data point. So this is typically done through a prediction function h, which has 2 inputs, the data x, and some parameter theta, which will be an RD in this talk. So within machine learning, in the last like 20 years, people have considered mainly 2 types of prediction functions. The first one is basically linear in the parameter theta, but it can of course be non-linear in the inputs x through the use of the feature vector phi of x. And the classical example is advertising, where phi of x is a pretty large vector of zeros and ones, like encoding your navigation history, but there are many applications of linear models in speech, bioinformatics, and so on. So this will make our life, this makes our life easier, but in many problems, people want to go beyond linear models, and this is where neural networks come in, and a classical application is in computer vision, where the input is an image, and y is the output. And for those problems, linear models are not state-of-the-art anymore, and people now use a sequence of linear plus nonlinear activation function models, which are based on that. And those are neural networks where you start from a linear model, theta 1 transpose x. So you combine your inputs linearly, take some non-linear activation function sigma, and then go on for a while, and you get R layers. And this is the so-called deep neural networks when R is big. Okay, so here you see an example with only 2 hidden layers. So keep in mind that if you just consider the last layer, theta r, that this is a linear model, but this becomes a non-linear model when you start to include the first layers in the process. So the way learning is done is by formulating this as an optimization problem where you want to minimize a regularized version of some empirical risk, where you have some data fitting term. So you have a loss function between yi, the label or the output, and your prediction. And you can think of L as being the logistic loss, like we will see today, or the square loss. So essentially a convex loss in H. So this is typically seen as a weak assumption, like most losses for learning are convex. And you add some regularizer to avoid overfitting. So this is the way machine learning is classically cast as an optimization problem. But of course, I will come back to that later in the talk. This is just a mean to an end. The real goal is to do well on unseen data. Okay, so I will often call this test error the expected risk, which is unobserved because you don't observe the distribution of test points. And this will be called the empirical risk. Okay, so this is a classical issue that we want to minimize the expected risk, but we only have access to the empirical risk. All right, so this is an optimization problem. When is it convex? Okay, so sufficient conditions for convexity are to have a convex loss. And again, this is a weak assumption, but typically you need to have some linear predictions. Okay, so this will not work for neural networks. So what are the positive consequences? There are two of them. First, as soon as you go convex, you get a long sequence of efficient algorithms, which are typically gradient-based. So of course, they can also be defined for non-convex functions. And in fact, we use gradient descent in the non-convex framework. But once you're convex, they go with quantitative analysis, both in terms of runtime, okay, the time it takes to optimize, and also in terms of prediction performance on unseen data. Okay, so there's a long sequence of work. You can do acceleration, you can do sampling, and so on. So this is like one part of the what I call the golden years of convexity in machine learning, which I make start at 1995 with SVM, and I ended up this year because I had to choose a year, and there's a lot of examples of those golden years. So this started with SVMs and kernel methods, but all the sparsity and low rank was clearly an important aspect of convexity. Optimal transport is a fashionable one at the moment. AGD is also one. There are many instances of like impact of convexity within machine learning, but the issue is we want to study in this talk neural networks, and this is will be typically non-convex. So when you want to analyze neural networks, okay, you have to decide what to study, and I will first limit the problem quite a lot by considering just only a feed-forward, fully connected network. So here an example with the 3 layers. So this is already a strong simplification. So in practice, people do some pooling layers, people do some convolutional layers. So this is much more complicated than this. And as you will see, I will make the problem even simpler by only having a single hidden layer. Okay, but keep in mind that this is already difficult because you have at least one nonlinearity. So there are 2 main difficulties associated with that problem. So the first one, which I already mentioned, is the fact that you get a non-convex optimization problem. And this will be the focus of the first part of the talk. And the second difficulty is that typically in those setups, people consider the over-parameterized regime, which is a situation where the number of hidden neurons may be quite large and typically much larger than the number of inputs. The dimension of the input is sometimes larger than the number of observations. Okay, so this will lead to potential issues in terms of generalization guarantees, and this will be the second topic of the talk. All right, so first in terms of optimization, so what can go wrong when you go non-convex? Many things. Okay, so the classical one is that local minima may not be global minima. Okay, you have stationary points, you may have some long plateaus. Essentially, everything depends on where you initialize the problem from. Okay, so this is very classical. So here a function in 2D with level sets, and you have some global optimum, local minimum, local maxima, stationary point, and so on. Okay, so when you optimize something like this, things are a bit difficult. So there are a lot of works, of course, of non-convex optimization. And the first idea is to try to get local guarantees. So if you can't get global guarantees, let's start to get local guarantees. And they're very nice sequence of works doing this and dating back from the optimization community, showing that essentially if you do gradient descent of some perturbations thereof, then typically you're going to convert either to a stationary point or to a local minimum. Okay, so this starts to be well understood, but this is only local. This will not tell you if you're, in my simple example, there or there. Then you may want to try to look at global guarantees. And as a first bad news of the day, this is impossible in general. So if you consider a wide set of non-convex problems, you will never be able to find the global optimum in a polynomial time. And the counterexample, okay, as well explained by the book in Nesterov's book, is that you take a flat function which is non-zero except in a small ball, and then to find the global optimum, you essentially have to find where the small ball is, and which is typically you need to find the point there, and in high dimension, the volume of that small part tends to be exponentially small. Hence, it's impossible in polynomial time to get global performance guarantees. This being said, who cares about such a function? Okay, so typically the hope is to optimize something nicer, and this is what people considered, and looking at the special case of neural networks. Okay, so two lines of works have been considered. The first one by Czarmanska and colleagues, where they exhibit a class of functions for which essentially all local minima are equivalent in terms of energy. So if you get trapped in any of those, it's okay if you get close to the performance of the global optimum. The issue here is that the model is very general and has too much independence to be really relevant for neural networks. A second line of work, which is also very interesting, is trying to get conditions under which there is no bad local minima. Okay, so essentially, only one local minimum, which is the global optimum. And the very nice work by Soltanol Kotabi, which is doing this, but this work has to reduce the scope by having quadratic activation functions. And in practice, you want to go beyond quadratic. So in this work, in this talk, I'm going to consider, as I mentioned, a single hidden layer neural network. So I have two sets of parameters. I have the input layer θ1 over there. I have the output layer θ2 over there. So since I'm considering a single output, θ2 is a vector and θ1 is a matrix whose dimension is number of inputs times number of hidden neurons. And the key insight behind our work is to considering H here as a sum over all of the hidden neurons. Okay, sum over J will always index the hidden neuron. And the key here is the fact that all the parameters associated with a neuron, J, is only appearing in one element on this sum. Okay, you have a sum of separately parameterized functions. So the way to formalize it is to see that your prediction function H is an average of functions, and each Wj here only depends on a single neuron, and there's no interactions between two hidden neurons. So if you were to go, but what's happening there? Okay, if you were to go towards more layers, then you would start to have sharing of parameters, which is what multiple layers are made for. But this will break this nice separable assumption. So here, for this talk, Wj is a vector composed of the input layer for neuron J and the output weight for neuron J and the input weights for neuron J. This is displayed at the below. So the main insight, do you know how to remove this? I drew something, but I don't know how to remove it.
It should be some cancel.
It's not me. Somebody did it for me, no?
Yeah, who knows? I mean, the ones who are spying.
This is very funny. Okay, thank you. So yes, so the main insight behind our work is trying to consider the fact that we have an average of functions, and when you go to the over-parameterized regime, when m gets large, the idea is to represent this empirical average as an expectation over a density, okay, with some over a measure with some density, and you go from this set of Diracs to a whole density. Okay, so this is very classical within statistics, and this dates back from Bach, and the idea to go from a large set of atoms to a continuum of atoms. So the key here is that you have made your nonlinear representation in W here. This is nonlinear in W because psi is nonlinear in its parameters to something which is linear in your measure. Okay, so since you have a convex function, a convex loss, which again is a weak assumption, you have essentially convexified your problem by changing the way you represent it. Okay, so this is the first idea which one could explore. You have made your problem convex in mu here. But the problem is that this is convex in an infinite dimensional vector space, and hence it's hard to do optimization on that space. And for this, people have considered Frank-Wolf techniques, which are made for learning over like convex hulls of many vectors, potentially infinitely many. But the issue, and what I've shown like in a recent work, is that to do the so-called Frank-Wolf steps, to see which neuron to add next, you have to solve a problem, which happens to be NP-hard. So essentially, you replace a non-convex problem, which is difficult, by a sequence of hard and non-convex problems. So this is not really getting anywhere. And in a way, this is not what people use in practice. What people use in practice is really to represent our measure mu as a finite set of particles, we call the WJ's particles, and do gradient descent, which is essentially backpropagation. So now there are a few questions we will try to tackle in this talk, related to this number of particles going to infinity. The first one is, where does it converge to? Okay, so when you get more and more particles, so this is often called the mean field limit of the problem. Then once you know what it converges to, can we show something about the behavior of that object? Okay, in particular, can we get global convergence to the global minimizer? And in the second part of the talk, how can I make sure it does predict correctly? Okay, so those are the three main aspects I'm going to consider now. Okay, so this is a joint work with Lenaik from 2 years ago. So just to remind you of notations, optimized over a measure, mu, I have a loss, okay, and this is my average of predictors. And the goal is to minimize the loss, okay, given some finite number of particles, W1 to Wm. So I'm going to consider the gradient flow, which is simply an ordinary differential equation where you go down the negative gradient of Fm. So just look at the steepest descent direction. And why we are looking at this is to make our life easy. Okay, so it's known that if you know how to deal with gradient flow, then you would know, it gives you a good hints on how to deal with algorithms. Okay, then two algorithms come to mind. First, gradient descent. Okay, you can see gradient descent. If you take gradient descent and take the limit when the step size goes to 0, you get back to the gradient flow. And this is true as well for stochastic gradient descent. Okay, so in a sense, whenever you want to first study some dynamics of optimization, the gradient flow is the first good idea. Okay, so as I will show later, then you have two possibilities for the choice of the loss R. Either you take the expected risk, and then you can, if you do a single pass stochastic gradient algorithm, then you get some convergence of the testing risk. Okay, this is a classical single pass LGD framework. But if you want to do full gradient descent on the empirical risk, then you would convert to the global, to the minimum or stationary point of the empirical risk, and then you will need to make sure that you do well also on testing performance. Okay, this will be the topic of the last part of the talk. In this part, I will only focus on the gradient flow. Okay, I have some gradient flow, and I want to show that it's converging. So what is the limit when m tends to infinity? So it has a name. I don't want to spend too much time on it, since this would take me like a full seminar. And it does converge to what is called a Wasserstein gradient flow. There's actually a gradient flow with a Wasserstein distance as a metric to define the gradient flow. And this, there's several works doing a similar thing. This started with Nintendo and Suzuki in 2017, then Lenaik and me, and also Andrea Montanari and colleagues, and as well as teams from NYU. So if you want to know more on gradient flows, there's a very nice book by Ambrosio. And so for today, I just want to highlight the fact that when M goes to infinity, this tends to a well-defined mathematical object which we can analyze. Okay, it is called the Wasserstein gradient flow. So now, in terms of convergence, so what we can show, and here I put only the informal theorem to make the slide easy, and you can look at all precise statements in the paper. But what you can show is that, in fact, the Wasserstein gradient flow does converge to the global optimum. Okay, if you have some assumptions which are met. Okay, so let me describe those assumptions, and the two assumptions are homogeneity and initialization. You cannot expect any gradient flow to converge to the global optimum. Okay, there have to be some assumptions, and there are some technical assumptions which I consider as weak, which are hidden in the paper. But the two main ones which I want to convey today are homogeneity and initialization. So what do I mean by homogeneity? I mean that my local functions, psi of w, have to be homogeneous with respect to all of the parameters or only one of the parameters. So for example, if you take neural networks, which is the motivation behind this work, if you take the two set of parameters for a single neuron, you have theta1 input weights, theta2 output weights, and you always homogeneous with respect to the output weights. Okay, so this, our result applies to those cases. But if you take sigma here as being a so-called rectified linear unit, so the ReLU, which is a positive part, then you get full homogeneity with respect to the parameters. And this will lead to benefits later in the talk. So here, the key assumption is homogeneity, which you need and which highlight one beneficial aspect of the ReLU, is that it's a bit more homogeneous than the others. And this helps us to prove our result. So it's the first condition. The second condition is to have the initial neurons to be well spread in all directions. So this is a common practice in neural network training. You take your neurons, you generate them with uniform Gaussians, okay, which you renormalize in various ways. By the end, the directions of the neurons are all well spread. And this is what we need for our result to hold. Right, so let me emphasize in one weak point of our result is that it is only qualitative, in the sense that what we say is that if the number of neurons is large enough, we converge to some flow, the Wasserstein gradient flow, and that flow has good properties. We are not able to say anything related to the number of neurons you need to reach this limit, okay, how big M needs to be. And we cannot, at the moment, give you the rate of convergence of the gradient flow, okay, in terms of time. Okay, so this is really qualitative. But as you will see in the simulations in a moment, it does behave very well in applications. And we hope that we should be able to get some good results, quantitative results at one point. So let me give you some very simple examples. I'm going to consider like the ReLU network, where I'm going to generate some data from 2D. So I have two-dimensional data, and I predict and I generate the label from neural networks with 5 neurons. Okay, and I'm plotting in the plot here the directions of the input neuron times the weight of the output neuron. And this, given the homogeneity of this function, is a good. It almost gives you the entire up to a sign, gives the entire knowledge of the neuron. And so here, I know that my data were generated with 5 neurons. Okay, so now I'm learning with either 5, 10, or 100 neurons. We know that we can reach the zero loss, zero risk with any of those models. Okay, each of those models are expressive enough to reach zero training loss. But as you can see, if you launch the gradient flow, okay, with only 5 neurons, then you get stuck. So you are not able to reach the true directions, which are the directions in dashed. Whereas if you take a lot of neurons, like in here, then our results suggest that you should converge to the correct neurons, which you see here. And what is amazing is that even if you just double the number of neurons from 5 to 10, you already get a very good performance. Okay, so we can account for this because this is a case where M here is very big, but we still cannot account for that. I even have some small video to see the dynamic.
So there is a question, Francis.
Okay, that's good. While I show the video, you can ask a question.
Adil Salim.
Yes. So I have a question. Have you tried to prove the same theorem, but in discrete time? So M infinite, but discrete time.
That's a very good point. So we consider going from gradient flow to gradient descent, which is essentially, I think, what you mean. And yes. We are not able yet to get anything concrete. But I think it shouldn't be too difficult. Okay, so if you're just willing to have convergence, okay, and in a qualitative way, I believe it's possible. Okay. With the similar tools. What is hard is to go from qualitative to quantitative.
Okay, thanks.
Yeah. So as you can see from the video, so dynamics is very complex. Okay, so you oscillate and then you end up converging. All right, so this is for convergence. Okay, so as a summary of the first part of the talk, what I presented is if you start with a prediction function h, which is a sum of terms which are parameterized independently, example like neural networks, then if the number of neurons go to infinity, the gradient flow will converge to the global minimum of your risk, which is over there. Okay, so the risk has to be convex. Again, there is no quantitative results, and we need a well-spread initialization, like uniform in all directions. So as I've mentioned, this can be applied, you can imagine applying the gradient flow to the single pass AGD. Okay, again, single pass AGD, if you let the state size go to 0, will convert to the gradient flow, of course, with many other assumptions, but this is to me the gist that you should remember. And you end up converging to the minimizer of the expected risk. Okay, so it's well known that single pass AGD will never overfit. Okay, in fact, it tends to underfit. So in most applications, people do more than a single pass. This is what we're going to consider now. If you do multi-pass AGD or full gradient descent, now you're going to minimize the empirical risk. So I'm assuming I have n data points, and I minimize the risk computed on those n data points. And then you converge to the minimizer of the training risk. Okay, but the question is, does it overfit? Okay, and if you consider classical like statistics, if the number of neurons go to infinity, the number of parameters go to infinity, have a finite amount of data, there should be a problem. Okay, so it may overfit, and the goal now is to try to study why it's not overfitting and can be characterized where the gradient flow converges to, so that we can prove that it's actually generalizing correctly to unseen data. So this is what's going to be the last part of the talk. So I'm going to consider what is called the interpolation regime. Okay, so what do I mean by this? So as I've mentioned, I'm minimizing some empirical risk, which is the average over my training data. Now I have n data points, and my function is parameterized by m neurons. Okay, so two key quantity. So as soon, in fact, it should be m when m is very large. In fact, it should be like the number of parameters with h is like m times d plus 1. So as soon as the number of parameters is bigger than the number of observations, you should expect that you can fit anything. Okay, so here it should be like md and not m. But anyway, m goes to infinity, so it doesn't make a difference, but there's a small typo there. then if you get a lot of neurons, you should expect to find some functions H, and in fact, many of those that will totally interpolate your data, which means that for all I, so all training data points, H of xi is equal to your label. Okay, so this is well adapted to regression risks, but if you do classification, like I will do soon, then simply the loss is 0. Okay, so if you assume that the loss is always non-negative, then you interpolate if you manage to get 0 loss. Okay, so in the classification regime, if you predict perfectly. Okay, so this is a regime which has been studied in terms of optimization by several papers recently. Okay, so when you know that this is true, okay, that you at optimum there exists an edge which has 0 loss for everybody, things go faster for optimization. This is what those papers are about. But what I want to focus on today is where do we converge to? Okay, so there are many H which will satisfy that. Okay, infinitely many H, a whole vector space of such H's. And the question is, where do you converge to? To which one do you converge to? Okay, so this is often referred to as the implicit bias of gradient descent, or AGD if you use like the stochastic version. And so here's the take-home message of the talk, and it's not my result. Okay, so our result is like this is like folk knowledge plus very nice papers by the group of Gunasekar, Srebros, Rodri, and colleagues, showing that whenever you use gradient descent, okay, you're essentially having like a prior on the L2 norms of your parameters. Okay, so here my parameters are the theta2 and theta1. So whenever you use stochastic gradient and you interpolate, you should more or less get to some minimum Euclidean norm solution. Why do I say more or less? Because for the square loss, you would assume this would be easy to show, but it's quite difficult. Okay, in fact, this does depend on where you start from. So you get like typically up to a constant factor of the minimum L2 norm solution, but you don't get the exact minimum L2 norm solution. But a key contribution of Gunasekar and colleagues is that if you go to the logistic loss, okay, for classification, then this becomes quite easy. You can characterize precisely where you converge to. Okay, this is what I'm going to do now. So now I'm going to move to classification and take a step back by just looking at linear models and describing what Gunasekar and colleagues have done. So this is my logistic regression function. Okay, this is my loss. Now I have some, oh, it should be a theta over there, sorry. So I get linear predictions directly in X. And I'm going to assume I am in a high dimensional setup where D is very large, so that I know that there is some theta for which the sign of my linear predictions is the same as my labels. So this is what we call separable data. And for all I, there exists a theta such that for all I, this is strictly positive. So by renormalization, I can have strictly bigger than 1 by taking theta a bit bigger. So the key insight beyond the work of Gunasekar and colleagues is to realize that if you start to minimize logistic loss on that problem, this will diverge. Okay, so let me be more precise. Is that that function is always positive. Okay, so the log of 1 plus exponential minus u is plotted in green over there. So it's always a positive function. Okay, and if this is true that you have some separable data, then you can check that the u over there will always be on the positive side for some elements, for all elements. So if you drive the norm of theta to infinity, then you will reach the minimum over there, okay, the infimum over there. It's one of those examples where the infimum is not attained. Okay, so you're going to, the green curve will push you to infinity. This is to be contrasted with the hinge loss in red, for which you will only need to be bigger than 1, and then no need to send the theta to infinity anymore. Okay, so the key here is that for logistic loss, since it has exponential tails, you will always push towards infinity. Okay, so here, 0 is the infimum of the risk, and it's attained for an infinitely large norm of theta2. This is like unknown, but the key insight from Soudry and colleague is the fact that although gradient descent will diverge, it will diverge because the infimum is attained at the infinitely large theta. So gradient descent will try to get there. So it does diverge, but you can show that if you normalize it, right, L2 norm, then it does converge to the maximum margin separator. Okay, so how you define this maximum margin separator? You take all unit norm vectors. Okay, so this vector is unique norm, and among all those unit norm vectors, you want to make sure that the minimal value of this, okay, so which will be positive. So you want that this is as large as possible for all elements. You want the minimum of those values to be as large as possible. This is a bit of an unusual way to present it. And if you remember your learning classes, or if you were born or as a researcher before 2010, you remember the separable SVM over there. You want to find the minimum L2 norm theta so that you have all of your predictions times yi or bigger than 1. This is the usual pictures from the year 2000, where you have some data which is separable, and you, among all the hyperplane that will separate your data, you select the one for which the distance between those two lines is as big as possible. Okay, it's called the maximum margin separator. And it turns out, and this is nicely showed by the Soudry and colleague, that if you run logistic regression, okay, on that problem, then you will diverge, but the direction will converge to this maximum margin separator. As a funny note, this dates back from '64, this SVM problem. All right, so now I'm going to apply this to my problem. Okay, so not consider a linear function over there, but my neural networks. Okay, so this is my prediction function. Okay, so which is positively homogeneous with respect to the parameter theta. And I'm going to consider the other parameterized regime. So because M is very large, I'm going to fit the data perfectly. So I am in the interpolation regime. So I'm going to consider two different regimes. The first one where I only optimize over the output layer, theta 2. Okay? And this will lead to the so-called random feature kernel regime. And one where I optimize over the two layers. This is the interesting part. So let me first go over optimizing with respect to the last layer. All right, so this is my function. The input weights are taken random, typically in the unit sphere, and they are assumed fixed as with respect to optimization. And I optimize over only my output weights theta 2. Okay, so here, what I have is a plain linear model where phi of x here is m-dimensional. I have one feature per hidden neuron, and this is my feature. Okay, so I'm back to linear length, so things are easy, and I can apply directly the result of Soudry, and I know that I should converge to the minimum L2 norm separator. Okay, so here only the minimum L2 norm of theta 2. Okay, so theta 1 is fixed, so I should converge to the minimum L2 norm of theta 2. So what does it converge to? Now I have to analyze linear models when the number of features go to infinity, okay, like this. And this is what kernels are made for. Okay, so what is a kernel? This is defined as the dot product of your features. Okay, so here my feature vector is m-dimensional, which is described over there. So if I take the dot product, then you get this nice average. Okay, this nice average, sum over all j's of j's features for x, j's features for x prime. And here, the nice aspect over there, since you generate the data ones randomly in ID typically, then this empirical average will converge to the expectation. This is also called random feature kernel by Neil and Raimi and Recht. So it's typically used in the other direction. I have a kernel and I want to approximate it, and I approximate it using some finite number of random features. So here we use it in the other direction. We want to see what's happening when m goes to infinite. So let's try to study this kernel, because this will tell us the type of functions we may learn. And so this is, as all kernels, this leads to some reproducing kernel Hilbert space. Okay, so if you want to know more, there's a nice book by Shulkov and Smolar. And long story short, whenever you have some RKHS, the functions you're allowed to explore are very smooth functions. So if you are in D dimensions, they need to have D over 2 derivatives at least. Okay, so yeah, D over 2D derivative or D over 2 derivatives. Okay, so this means that those are very smooth functions. So you cannot expect something which is very with lots of non-smoothness. And what we obtain with LeNaik, with a recent paper of this year, is that when the number of neurons goes to infinity, then we converge to the minimum separator in that space, okay, with the minimum RKHS norm. Okay, so here, in that case, we get some quantitative analysis, okay, because in fact we have a linear model, so we are back in the convex world, so both in M and T. And so first aspect. Second aspect, note that letting M go to infinity is useless in practice. The reason being that you get a kernel trick. So as soon as M, okay, is bigger than N, you're better off by using the kernel trick and optimize over the usual dual parameters, which will be more efficient. Okay, so M go to infinity here is more like an exercise to understand what's happening when you let the number of neurons go to infinity. I should note that Montanari and colleagues have a nice related work in the context of double descent, and I'll come back to that in a moment. All right, so this was for the kernel case when you optimize over the, only the output layer. So before going to the all layers, I need to do a small pause on function spaces. So the RKHS norm, which I've just defined, based on the kernel, can be defined also in this way. It's a classical exercise in RKHS theory. So if you take a function f, then it is squared RKHS norm is the infimum over all L2 over all L2 norms, like squared L2 norms of some function A. Okay, so here SD is the D-dimensional sphere, D tau is the uniform distribution on the sphere, and you represent F as linear combinations of ReLUs. Okay, so this is exactly our representation of our functions are an expectation about some measures of some neurons. Okay, and over all those decompositions, you select the one with minimum squared L2 norm. Okay, so this defines the norm. This is exactly the RKHS norm. Again, the space of this RKHS is composed only of smooth functions. Now, if you change one line, so you remove the two, okay, then this defines what is called the variation norm, okay, which is no more the L1 norm because now I don't have any squares over there. So among all functions which can be decomposed as a continuum linear combination of hidden neurons, I select the one with the minimum L1 norm. Okay, so this is much larger because of the relationship between L1 and L2 norm. And this is composed of functions which may not be smooth. In particular, a single neuron is okay. And as I had shown in earlier work, those spaces, because of the L1 norm, will tend to be adaptive and to learn to adapt to some linear structures like dependence on a small number of parameters, for example. So now what I'm going to show is that if you optimize over the two layers, you're going to go from that space to this space. So let's see the formal result. So this is my prediction function, again, linear combination of neurons. And now I optimize over all weights, okay? So why do we go from L2 to L1? So the heuristic, which is very heuristic, is that, again, if you do HGD or gradient descent, you should converge to the minimum L2 norm of your parameters. And now my parameters are θ2 and θ1, okay, as the product. So the L2 norm of a square is like the L1 norm, okay? So no. Yes, the L2 norm of the the L2 norm of the product you can see as the L1 norm of the whole. And if you want to know more, you can look at the paper. So what do we show? So we show that, again, I put here informal to make sure that this remains correct. There are some technical assumptions, but those are limited. that the gradient flow does converge to the function that does separate the data. Okay, this is normal, but now with the minimum variation norm. Okay, so this will, among that space of functions, this will select the one with minimum norm, and hence this will not overfit. Okay, it's not taking any function which can separate the data, it takes the one with minimum norm. And what we show in the paper, which I will not report here, is the fact that it is adaptive also to some linear structures. It does adapt better than the kernel case. As a side note, if you want to optimize under this variation norm as a penalty, I don't know of any convex algorithm to do that. Okay. Although it's a well-defined norm, it is defined as the L1 norm on an infinite dimensional space for which there is no known like polynomial algorithm, and using like finite number of particles, although it does not lead to any convergence guarantees in terms of quantitative guarantees, it does lead to qualitative guarantees in the sense that if M is large enough, this will converge. Also, on the side note, if you know about double descent, which is a nice framework like posed by Misha Belkin and others, where they see that if you increase the number of parameters, your performance will diverge as the number of parameters hits the number of observations and then go down again. Then what we show is that the end of the double descent curve is well taken care of. Okay, so if the number of neurons is infinite, then you get this, you get the minimum margin separator. So let's look at some video, okay, nicely made by Lenaik. So here I'm going to show a problem in 2D, okay, with some intercept, some constant term. So now I'm plotting in 3D because there is like the 2 dimensions which are linear plus a constant term. I'm plotting this on the left, and on the right I'm plotting the space of predictors, how well I am separating data. As you will see, as the neurons move a lot, the prediction will also move a lot. Let me run it. Okay, so here some neurons don't move because the bias term was so high that the gradient remains 0. Okay, so some remains constant but do not contribute to the sum. And as you can see, neurons move in some wild ways, and you end up so converging to a separator which has some significant degree of non-smoothness. Okay, so this is like a piecewise. This has some piecewise fine boundaries. So at the end, the number of active neurons after they all cluster together is finite. Okay, so this is classical. You penalize by some L1 norm, you should get like a finite number of atoms. Okay, so this is one example of running the algorithm on 3D. Now to give some insight in the comparison between L2 versus L1. Okay, so here we are similar setup. We are doing like binary classification, plus versus minuses. On the left, this is training only the output layer. Okay, so the input layers are random and fixed. On the right, they are initialized as random, but they are optimized over. Okay, so on the left, kernel. On the right, full learning. And as you will see, on the left, you will get smooth boundaries, whereas on the right, you will get like non-smooth boundaries. Okay, so these are the key effects between optimizing all layers. On the right, you're going to learn some features which are important for the problem, whereas here on the left, you only rely on the random features, and you only get smooth functions. Okay, so this is one key insight is that when you train with infinitely many neurons, you get to different regimes, and this is obtained by using the implicit bias of gradient descent. All right, so one very basic test error plot, just to highlight adaptivity to linear structures that you have when you optimize over all layers. So I'm considering like very toy example where I want to separate data in 2 classes, and the first 2 dimensions are like this, okay, well separable. Whereas I add some like 13 dimensions of noise. I could make more than 13. That would not make a difference. And as you can see, if to do well on that data, you need to do some variable selection. You have to adapt to find the subspace spanned by the first 2 variables. And if you compare the two algorithms in test error, then if you optimize over both layers, you do significantly better than if you optimize over only the output layer. This is just to highlight the difference on some toy data. Right, so to conclude, try to provide some qualitative analysis of gradient descent for two-layer neural networks. And what the key results are some global convergence results when you let the number of neurons go to infinity. Okay? And in the second part, convergence to some maximum margin separators in well-defined function spaces. Okay, this is the key here, is that we know where it converges to, but this is unfortunately only qualitative. Okay, both in terms of number of neurons and time to achieve the optimum. So in terms of open problems, you may expect that the clear open problem is to get some quantitative analysis. Okay, and I hope to get some help there from people attending today, because it is really something where in practice, so if you start with data which is like occupying major portions of the space, then the number of neurons is small, and the time it takes is reasonably small as well. So we see here that we get something which is behaving very well, but for which we can't get a handle in terms of quantitative analysis. And of course, here I've just focused on multi-layer, two-layer feed-forward nets, but going convolutional would be important to highlight the implicit bias occur when you use convolutions, and of course, extensions to deep nets beyond the single hidden layer. Thank you for your attention.
Well, thank you very much, Francis, for a very nice talk. Yeah, very nice new results, very nice illustrations. So now it is time for questions. So we are happy to take questions from the audience. Okay, so let me start and ask you. So of course, the very naive natural question would be, okay, if you want to make the step from 2 to 3 layers, what will be the main difficulty?
So what you can do is, first you can, if you let both layers go infinitely wide, then you can derive a set of partial differential equations that you should satisfy. And it has been done by, I forgot whom, but somebody has done it.
Okay.
But the issue is that it's very hard to analyze what those PDEs are doing.
Ah, okay. Yeah.
So, and you get some PDEs, and it's very hard. So one possibility here is related to some work that I think Sami Benjo and colleagues have done. They have shown that if you run some deep networks, typically neurons don't move away significantly from their initial values for some layers. Okay?
Ah, okay.
So for the middle layers, typically you stay close to where you are, whereas for the first layers, you tend to move quite a bit. Okay? So the hope is that you need to consider everything moving only for a few layers, for which you could imagine using results like this one. Okay. Clearly, if everything is moving, it's difficult, and this is why it may require tools which are beyond optimization. Okay, tools from PDEs, I think, will be welcome there. Because so the classical tools that I know of did not work on that one.
Okay, thank you. So we have a question. We have two questions. So Alain,
yes.
Could you please introduce yourself first?
Yes. So I'm Alain Rossier. I'm doing a PhD in Oxford under supervision of Ramakant, and I have a question actually on the dynamics, because can you frame the problem as a mean field Langevin equation somewhat? I know that the problem is not really stochastic, but in that space there exists some quantitative convergence results, right?
That's a very, very good question. In fact, in a longer version of that talk, I had a slide about that. So they're very nice. There's some work by Songmei and Andrea Montanari showing exactly this. So if you add to your gradient some noise, okay, and then you get like you convert to some diffusion, for which you can prove some guarantees in terms of the number of neurons. Okay, you need to approximate the diffusion. But the issue is that when you add the noise, you add some bias, and you don't converge anymore to the global optimum. Okay, so the object you converge to, you know that you converge to that object at a given speed, but what it means is unclear. Okay, so the main issue here is that, well, it is difficult because at the optimum, the measure you converge to is singular. Okay, so this is what makes it super hard. So if you can show that your measure remains absolutely continuous throughout optimization, it's over. You get linear convergence. Okay, so what's difficult, you want to converge to a singular point, and adding noise will remove that possibility. Okay, but by making the problem a bit easier, you don't converge the correct solution. But indeed, you can use like diffusion as well, and I think other people than Montanari have done it. But the difficulty is to let the amount of noise go to zero.
Okay, I see. I just have a follow-up question, actually. So this is considering exogenous noise, right? So you consider noise that are outside the model, and you do it.
Yeah.
And what if you consider the endogenous noise implied by SGD, so by choosing random samples? That is more, yeah.
That's a good question as well. But so when you add, so if the step size of gradient descent is gamma, okay, to get to a diffusion diffusion behavior, you need to add noise with standard deviation square root of gamma. Okay.
Yep.
Whereas if you do SGD, since you add noise to the gradient, the noise is multiplied by gamma. So since gamma is small, you get the noise is not big enough to get to the diffusion behavior.
Okay.
So it's the natural noise of SGD is not correct.
Okay, thanks.
Sergey Dorgov. Sergey?
Hi. Yeah, thanks, Francis, for the interesting talk. I might have missed something, but you wrote your network as a bilinear function or something like θ2 times θ1. I was wondering if this function is actually discontinuous, or maybe it's actually continuous, but the gradient is so large that you just treat it as discontinuous.
I think you mean the gradient is discontinuous, I agree, but this function is not discontinuous.
Oh, I see. You have an indicator function on top of θ1x. Okay.
Yeah, so
it makes sense.
This is, maybe I should have made this more precise. This is the positive part. Okay, so this goes like this. So the gradient is discontinuous, but this is a continuous function, and so this gets technical. But for those functions, to be able to define the gradient flow correctly, we need to assume that the measure we work on has some density. Okay, but this is like gets technical, but we can deal. So gradient flows with non-differentiable function. It's possible if you have some like convexity properties, and we have those. That's it.
Okay, thanks.
So there was another question if you can do 3 layers, but this is what I asked at the beginning. So then we take Olivier Grisel.
Hello, thanks for the talk. So I'm a software engineer at Inaria. My question is about the second result is about the non-smoothness of the decision function at optimal. Does it depend on the use of the logistic loss, or can we say something similar for other loss functions such as hinge loss or squared hinge? Or
no, okay, so yeah, so it does depend on one thing, which is the exponential tails. Okay, so if I go back to my loss, my loss, and as a funny part, I took that plot from my talks from 15 years ago. Okay, so at the time it was fashionable to look at losses, so here what counts is the fact that you get some exponential tails over there. Okay, so if you take hinge or square hinge, and then they get to 0 exactly at 1, and then they will not drive the norm to infinity. So you do need some exponential behavior. So this is for logistic loss, and for the exponential loss, this will work as well, but not for the hinge loss.
Thank you. I have another question about a previous slide where you rescaled the coefficient of the model. Can you say anything about the test loss of this rescaled predictor?
Which rescaled? Can you?
You say here that it converges to the maximal margin separator, when you rescale the coefficients here.
Yeah. But so here, I think you can show that that norm, the norm over there, which you rescale theta with, goes to infinity. Okay, and since you predict as a sign, the sign of your predictions, then the magnitude does not matter.
For the test error, but for the loss.
Oh, for the loss. Okay, so here this is only in terms of, since we are on the separable regime, it's always zero loss. Okay, and we count the norm of the predictor. So this is no. So here I should have made that more precise. Is that so here anyway, to make the logistic loss small, you need the norm to go to infinity. And in the paper, we quantify how fast it goes to infinity, but I forgot the details.
Okay.
So, you have another question? Mathieu Bessanson.
Yeah. Hi, can you hear me?
Yeah.
Yes.
Great. Hi, yeah, I'm a PhD candidate at INRIA also. I had a question on the parallel between gradient descent and gradient flow. Have you considered doing something similar with higher order differential equations? So it's well known that Adam, for example, mimics like some second order acceleration. And have you looked into that?
We haven't, but I know some people are. So personally, okay, it's already hard with the gradient flow to get some form of quantitative analysis. And so we're trying to do as well as we can the gradient flow, but clearly going second order makes sense. Using momentum makes sense, but add momentum plus renormalization makes sense. Yeah, it does totally. In fact, it would be nice if some good flow equation would have similar behavior for Adam, which I'm not sure. It exists already, but no, it's a good point. I think so. Here, Adam has two things. It does renormalize, which I think is really important there. The momentum aspect, I guess, may not be. I would think it may not be as important, but it's more of a personal taste at the moment than like concrete conclusions.
Okay, thank you.
So Manuel Bomze from Vienna.
Hello, Francis. Thank you very much for your interesting talk.
Hello.
I have a very low-level question, and I apologize in advance if it's completely nonsense. So what you have shown in your theory is that you can exchange under some condition limits.
Yes, we can. Yeah, we can.
So failure of exchanging limits always means a lack of a deficiency in uniformity of the convergence. Can you somehow identify at the very low level what goes wrong in general, so that we need these strong arguments?
I think what goes wrong, and this will show how weak our result is that so the principle essentially when you show the global convergence is that at every time steps you show that you have mass of neurons everywhere with non-zero density. Okay, so this is the argument. The argument is really that everywhere, at every time and everywhere, when you need some neuron, there is somebody there, okay, with potentially very small probability. The issue is that probability, okay, as time goes on, goes to zero very quickly. Okay? This is the problem there, is that you want to have some mass around to help you when you need it, but at the end, you want that mass to go to zero to converge to the singular measure. And this is at the low level what our difficulties are, and try to go quantitative is really that. So the difficulty is how do you make sure that you have sufficient mass around to avoid bad stationary points. Okay, so this is right now our analysis. I think the way we do it, I don't see how we can escape that issue. So trying to go further, but really the key is that we rely on this classical like mass-stationary gradient flow property that if you push mass through like continuous or differentiable velocity field, you preserve densities. Okay, this is what we use, and this is how to make quantitative.
Thank you.
Okay, thank you, Manuel. So we have another question. Why is Aziz young?
My question. Oh, yes. Sorry. Oh. So hi, thank you for your talk. So my question is, for generalization, is it better to have smooth or non-smooth predictors? You presented two norms, so is one of them better than the other for generalization?
That's a good question. So I think the problem here is, so in terms of, I think in my paper from 2017, I'm computing that the various like mathematical complexities of the two norms, and they are similar. What differs is approximation error. Okay, is that because the RKHS has smooth functions, okay, you need a very large norm. You need, if your problem is not smooth, okay, you need to really get to the borders of your RKHS, and this will have a cost, because you need the norm, that theta norm, the H norm, to be very large. Whereas if you take the space of non-smooth functions, you can deal with a much smaller norm, and hence a much smaller number of parameters. It's really a problem that RKHS are spaces of smooth functions. And if your problem is non-smooth, you can approximate it, because typically those smooth functions, those spaces of smooth functions are dense in L2, so you need a lot of a big norm. Okay, so this is the deficiency of RKHS is really that they are too small. Okay, they are efficient to work with. You can work on them in polynomial time through the representative theorem, but they are too small. Okay, so this is.
Thank you. Sorry. Oh, sorry if I. Yeah, okay.
I can't hear you.
Thank you for your answer. Okay, yeah, thank you.
Okay, thank you for your question. So, more questions? So everybody's happy, Francis. This was a very nice talk. We have a very nice discussion. So, comments, questions? Francis, can you hear us?
Yep.
Okay. Yeah. So the audience is happy and satisfied. Oh, there is another question. Vadim Kantorov. Vadim?
Hi, Francis.
Hi, Vadim.
Hi. So I wonder if I understand well, you have some minimum norm solution at the point to which you converge.
Yep.
And you have two different norms, right? So can you go the other way around? So imagine you want some other norm to reach some minimum norm solution at convergence. Can you derive a model and algorithm that would do that?
Very good point. So I think for the RKHS norm, it's so if you give me a kernel, okay, so as long as I can write something like that, okay, then I'm fine. So for all of the norms, it can be cast as something like this for a certain function. Here you can replace this wholly by anything. This would work the same, either with the L2 norm, square L2 norm with the L1 norm. Okay, so this for kernels, okay, as soon this will work very well with the sphere as soon as you have so-called dot product kernels. So if your kernel depends only the dot product between your two inputs, x and x prime, then you can find such a representation using like either Hermite polynomials or Legendre polynomials. so this is clear for the kernel case. For this one,
if not kernels, or some other function spaces. I don't know if it makes sense.
No, it does make sense. So essentially, so what you say is that what function spaces can I reach using like a finite number of particles? I think that's a very good question. And the answer is those spaces for the moment, but there may be others. Okay, I totally agree that we rely a lot on the fact that we have some linear parametrization with some measure. We use the variation norm of the total variation of that measure over there. But you could imagine other cases where the link between the f and its norm is a bit more complicated, still using the measure. That's a good point. No, that's yeah. That's in fact, this is also related to the fact that whenever you have some L1 norm, you have some sparsity effect. I think there is some recent work by Claire Boyer and others showing how when you get some nice sparsity inducing effect from those norms, but you would have to look at the work of Claire Boyer.
Okay, thanks.
Olivier, another question?
Yes. So sorry, I'm trying to think about what are the implications of this inductive bias. So it seems that at convergence, the non-smooth neural network decision boundary, the neural network is overconfident, like it's probability 1 or 0 almost everywhere because of the log loss. It seems fine for the test error, but it's very bad for test loss. The model calibration will be bad. But maybe the shape of the decision function is better. So it seems that there is some kind of trade-off that can be arbitraged by the early stopping or something. Can you say anything about this? Or?
I think here, okay, so I would not give too much like practical credit to those results. Because as you mentioned, you will never allow your predictor to go to infinity, okay, at training time. Okay, so you would stop before. You will either add some regularizer, okay, to avoid that, or you would like you would stop before. Okay, so here what you would expect is that if you do early stopping, okay, so you early stop at a position where the norm has not diverged, but the boundaries are of a similar shape. So this is like a problem that result that so it does consider the end of the learning curve. Okay, so typically you stop a bit before, and this is already difficult to understand what it means in the convex case. So I have like other work in the convex case with Lucas Pillot-Vivien and Alessandro Rodi, trying to understand when you do multiple pass LGD when to stop, okay, to avoid totally interpolating the data. But here in the non-convex setup, it seems much more difficult. But I agree, you should stop before. And once you reach that point, it's okay. So here, in fact, if you look here to do the plot over there, I had to use some tangent radial scale because this will go to infinity. Okay, so if I reduce the video over there, then I think they all get stuck to the unit sphere. Okay, because they're all diverging. Okay, so this is what should appear. They're all in the unit sphere because they have all diverged. Okay, so here on the left, here you have to keep in mind that there is some rescaling of the data of the radial scale.
Okay, but if you early stop, also the position of the decision boundary is not the same. So it seems that there is a trade-off between the calibration and the generalization from a test error point of view.
I totally agree that so here, and this is similar to the work of Soudry, Gunaseka, and Srebro, is that we study the end of the curve. Okay, so we wish we would be better and study so various position of the curves. So those are not the double descent curve. Okay, those are learning curves. Okay, where the x-axis is the number of iterations, and trying to understand what's happening before we reach like t being infinite, t number of parameters, t number of iterations. That would be better. But this is work to be done in the future.
Okay.
Okay, thank you.
Yeah, sorry, just so that I thought about something. It's Alain again. And because you mentioned actually that the projected parameters actually they are so the minimum norm solution. Are you considering writing the equation in terms of the dynamics in terms of the projected parameters? So you project everything to the sphere and you look at what is the projected gradient flow instead of the gradient flowing like this more in this bigger space?
Oh, in fact, the proof is being based on projection on the sphere.
Oh, okay.
So why we need homogeneity? Okay, why we need homogeneity over there? We need homogeneity so that we can normalize everything, okay, and get some. We go from a probability measure on the whole space to a finite measure on the sphere, and this is easier because it's a compact space, and things are easier because of that. Yeah. So in fact, it is very important to be able to go back to the sphere. This is why we need a lot this full homogeneity for that result. Okay. So everything is much simpler if you can go back to the sphere. Yeah. So that's important. And this is so this is key here. The ReLU makes our life easier. This does not mean that we could do the same thing. We could do the same thing with others, but this would require other tools. And but Lenaic, if Lenaic is there, I could comment. But we do need the homogeneity here.
Okay.
So, Francis, it is time to stop here.
Okay.
It was a very nice talk, very consistent discussion. Huge audience. So thank you very much. We will post a video on our website.
Okay.
And could you also send us your slides?
Sure, I will send you the slides. Sure,
yeah.
I'll do.
And so thank you again. Thank you very much. So my hope is to be able to organize next year, the same seminar series in Vienna, like in real. Then would be happy to invite you and to give another talk here.
Okay.
But, and this just means that we will go back to normality.
Hopefully.
Hopefully. So thank you, Francis.
Thank you a lot for listening, and have all a good week.
Yeah, all the best and a good week. Thank you. Thank you. Bye bye.
Thank you, Francis. Take care.